So we talked about the graphs of sine and cosine. They look very similar to each other, and they had like this like wavy periodic sort of thing going on where they just repeated over and over again. As long as you drew like the positive values on the graph, you could just copy the negative values since it repeats itself over and over again. And the same thing goes for tangent, which we started talking about. And the way I introduced tangent was showing how it was equal to sine over cosine, right? So we use that identity to figure out how to draw this graph, okay? Now we have these vertical asymptotes on our graph. Does anyone remember how those vertical asymptotes came about? Like why they're at pi over 2 and 3 pi over 2? Yeah, can't divide by 0. And cosine is 0 at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on, which is why we have all of these vertical asymptotes around our graph. Okay, that's kind of where we stopped here. We also drew last class a couple important points. So we drew a point at 0, pi, 2 pi, negative 2 pi, and all those values ended up being 0 because, well, that's how it kind of ended up, right? Okay, so we have points on the graph. Okay, part of me wants to go over how to like get the exact shape of this, but I don't think we have enough time for that. So what I'm going to tell you is tangent is an increasing function, okay? And that gives us enough information to get the shape of the graph. If you want to know why it's increasing, just plot a few more points, make it a little bit more detailed. But what I'm going to do is I'm going to make this an increasing graph. And to finish off that shape, what happens to a graph near an asymptote? What does a graph do? Yeah, it gets closer and closer and closer, but it never actually reaches the asymptote, okay? So if tangent is increasing in each of these sections, if I started at 0 and went up, I would go increase up, but never actually touch the vertical asymptote, okay? On the left-hand side of 0, since we're still increasing, tangent's an increasing function, we would just go down, 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 until we barely touch the vertical asymptote. Okay, so that's what we do in one chunk. Remember, tangent is a repeating function. Every single, I don't know, pi values, we get the same thing because sine and cosine are also repeating. So the same shape is going to happen in every single section. We're going to increase, get really, really, really close to both of the asymptotes on both sides. So we're going to go up, we're going to go down, up, and down. And this is what tangent looks like. It's a repeating function. It keeps repeating itself over and over and over again. And we have asymptotes wherever the cosine is equal to 0. Okay. Important things that I look for when I'm like taking a look at your graph on your test or quiz. I'm definitely looking for you to label the x-axis. So make sure you have like 0, pi over 2, pi labeled on the x-axis. There's nothing really labeled on the y-axis, so don't really worry about that, okay? One thing I'm looking for is, well, I want these asymptotes shown, okay? And just to make things simple for you, if you don't want to draw the other asymptotes, I'm really not going to care as long as you draw the 2 between negative pi over 2 and pi over 2. So that's what I'm looking for, okay? Another thing I'm looking for is this dot, especially in the center, okay? And finally, I just want that shape where it's increasing, getting really, really, really close to either asymptote. Okay, that's what I'm looking for. To make things easier for you on a test or quiz, I'm going to give you this list on what to draw whenever I'm asking you to draw the graph, okay? So I'm going to tell you to label the values in the x-axis. I'm going to tell you to label the values in the y-axis. I'm going to tell you what points to like clearly label. Okay, meant to use a pencil for this, okay? And I made a typo here, okay? Under 3b, it says label pi over 2 for tangent. Pi over 2 is an asymptote, so I don't know why I would want you to label a point there. What I really meant for you is to plot the point 0 at the origin for tangent. So that's what I was asking you to do there, not pi over 2. Okay. Finally, I do want you to show any asymptotes with those dotted lines, just like how I did it on the graph here. Okay. So this is all I'm looking for. Make sure you either memorize how to draw them on your note card, or be able to quickly reproduce them, right? I really do wish I had an iPad for this class, or when I was in undergrad. One time I lost all my notes for one class, and it was very, very sad. And I wish I had an iPad that stored it for me. All right, so we're going to talk about inverse trig functions. If you have an iPad, nice, you can use different colors for this. But let's just think back to these things. We talked about trig functions. I think we're all good with these. We haven't talked about inverse functions for a while, okay? So I'm gonna leave it up to you guys. What do you remember about inverse functions? Like what they are, how do you find them? How can we tell if something an inverse? Examples, anything like that? Yeah, we found them by flipping the x and y. Flip x and y. Anything else about inverse functions? How could we tell if something had an inverse? Yeah, like a graph. Not vertical, but horizontal line test. Good. I actually get mixed between the two, but we use the horizontal line test to test if a function had an inverse or if it didn't have one. Okay. What else? Any examples of inverse functions that you remember? There were two that we kind of spent a lot of time on. What's the inverse of log base 2 of x? It's been a while. Remember, it's log base 2. So 2 is the base.
Yeah. 2 to the something.
Yeah.
X.
Yeah, 2 to the x, right? 2 to the something. Yes. 2 to the x, these two were inverses of each other. And the reason they're inverses is because like you could like apply one to the other function and they cancel each other out, right? So if you saw log 2 in an equation, you could take 2 to the power of each side of the equation and they would like cancel each other out. They're opposites of each other, right? Even more in general, remember inverse functions are just things that cancel each other out, like addition and subtraction, right? Multiplication and division. If you ever see addition on one side of the equation and you wanted to like cancel it out, you would just subtract on both sides, right? So these are just things that we use to cancel something else out, okay? One more example I'll give you, x cubed and the cube root of x, right? These things are opposites of each other. They cancel each other out, okay? So we have a bunch of examples. Let's talk about what the inverse of sine is. Cosine, tangent, what are the inverses of these functions? Okay, so we have the most creative names for these. The inverse of sine is going to be called inverse sine, and the inverse of cosine is going to be called inverse cosine, and the inverse of tangent is going to be inverse tangent, okay? But we do have some notation, so we don't have to write inverse sine, inverse cosine, inverse tangent. And this is the symbol that we used. I think these might look a little familiar for those of you who have had trig before. Okay, inverse sine uses this kind of notation. We have sine, but we just have like a -1 floating on top, okay? Cosine, inverse has a -1 on top. Tangent inverse has a -1 on top, okay? Now, before we go on, there is something that is kind of important that a lot of people mistake this notation for, okay? So before we get into anything else, let's talk about this notation, sine square theta. What did that mean? Yeah, what did that mean again? Like, what did that tell us to do? Or, yeah, just take sine and square it, right? So this was the same thing as taking sine. Yeah, sine of theta and like squaring the whole thing. So like you would find sine of the angle and then you would square it. And that's just like a shorthand notation, right? Now, I'm going to tell you something that gets very confusing. And I think mathematicians just like to make things confusing every once in a while. Sine -1 theta. Oh my goodness. So sine -1 theta, that's not the same thing as sine theta to the -1. Okay. So even though the notation up top says we just take sine and square it, sine inverse theta is not the same thing as sine theta to the -1st power. So we're not raising something to a power here. All this is saying is sine inverse of theta. So this is an inverse notation, okay? I know it sounds a little crazy, but this is what we mean when we say sine inverse. Okay. Any questions so far? Okay, so when you read this, don't read it as sine raised to the -1. It's just sine inverse. Okay. Let's do an example and see where things go here. Okay. Take a look at this example. We have sine inverse of 1/2. Okay. Now, the way I like to do this is I like to think of it in like one of two ways. Okay. The first way I like to think of this is this question is asking me what sine inverse of 1/2 is, right? So sine inverse of 1/2 equals question mark, right? Okay. I like to do something very similar to when we did exponents. I just like to rewrite this in a different way. Okay. Since this is going backwards, right? Inverse functions kind of undo the regular function. Isn't this the same thing as saying sine of what equals 1/2, right? Inverse functions flip everything. It flips the x value and the y value. So basically what this is doing is we're taking the x value and we're moving it over to the y value side. We're moving the y value and moving it to the x value. So we're swapping the two. Okay. So whenever you see this notation, I always like to write on the side, sine of what angle equals 1/2. Okay. If you like thinking of things in words, another thing I like to think in my head is, okay, the sine of what is 1/2. Okay, that's another way you can think of this in your head. I like seeing it symbolically, makes more sense to me, but if you want to think of it, the sine of what angle equals 1/2. Okay. Let's take a look at our unit circles. What angle is the sine 1/2? Yeah, 30 degrees or pi/6, right? Because, well, sine is the y value of the coordinate. Sine of pi/6 is 1/2. Good. Any other angles? Any other values where the y value is 1/2? 5 pi/6, right? Sine of 5 pi/6 is also equal to 1/2. Okay, so now we have two angles. And if we go into negative angles and angles bigger than 2 pi, we have even more angles where the sine is 1/2, right? So I guess there's infinitely many answers to this question so far, right? Here's where things get complicated. I'm going to tell you the only answer to this question is 30, pi/6. Nothing else. Everything else is wrong. Every other answer is not the answer to sine inverse of 1/2. Okay. Any idea why? Why is sine? Why is inverse sine? Why does that only have one answer? Not quite. It's a good guess. Okay, it actually goes back to this thing right here, the horizontal line test. This is where things get a little bit more interesting, okay? So this goes back to the horizontal line test, and I'll show you how these two are kind of related, okay? Might not make much sense right now, but let's just flip our page and try to see why the horizontal line test tells us how many answers we have to this question. Okay, so we're going to explore why there's only one answer to inverse trig, okay? Let's start with sine, and let's just draw the graph of sine, okay? Now I set up the graph for you. I've put all the X and Y like labels on there so we don't have to spend too much time drawing this. And I'm kind of going to blast through this because, well, we went through the graphs like earlier, like 10 minutes ago. So remember, sine has a wavy shape. It goes up. Oh no, wow. Okay. It goes up, it goes down, and it goes back around. So it looks like this. Okay. And remember, on the left-hand side, it's basically like the same thing, but copied. Drawing a very bad sketch of sine. Okay. So we've drawn sine. Does this graph have an inverse? No, and why not? Exactly, right? This graph does not have an inverse, and I'll write that down, because it doesn't pass the horizontal line test. If we take a horizontal line and move it up and down, it's actually going to hit sine an infinite amount of times, right? It has an infinite amount of times where it hits that line. Since this graph goes infinitely to the right, infinitely to the left, it keeps repeating itself, okay? Wait a minute, we have an inverse for sine. We called it sine inverse, like we have a formula, like we have a notation for it, and we were able to like apply it to a certain question, right? So how does sine have an inverse, even though we just said it doesn't have an inverse here, right? Okay. We were strictly no, no. Mathematicians always like to find ways to kind of cheat the system a little bit. Okay, and this is what we're going to do. We're going to do something kind of sneaky. Okay, let's take a look at sine in between negative pi over 2 and pi over 2. Kind of highlighted it. All right, let me highlight it again so you guys can see the highlight. Okay. Does this graph pass the horizontal line test if I ignore everything else and just focus on that blue highlighted area? Yeah, right, it passes the horizontal line test, okay? What about between pi over 2 and 3 pi over 2? Yeah, right, passes the horizontal line test. And between negative 3 pi over 2 and negative pi over 2, that also passes the horizontal line test, okay? So what mathematicians have done is they realized, okay, what if we just focus on one of those highlighted parts and ignore the rest of the graph? Then we can find the sine of whatever we're taking the graph up, right? Okay, so what we're going to do, since the most important part of any graph usually revolves around 0, like 0 is a really important point for most applications, is we're going to do this thing called restricting the domain. Okay, you don't have to know that term, but basically what that means is we're just going to focus of the values between negative pi over 2 and positive pi over 2. Those are the only values that we're going to focus on right now, okay? So we're going to just think of sine in between these 2 points, okay? So when we're talking about sine inverse, the only part of sine that we're going to focus on is between pi over 2, negative pi over 2, and our graph is literally going to look like this, okay? This is the graph of sine that we will focus on for inverse functions. That's it, okay? This graph passes the horizontal line test. It has an inverse, and well, we can do inverse sine for these values only. The only problem is it only involves x values between negative pi over 2 and pi over 2, okay? So therefore, the only answers that make sense for inverse sine are answers that are between negative pi over 2 and positive pi over 2, okay? Any other answer will not work for inverse sine. Okay. I think what we should do is do a couple examples, okay? And I think it might not make too much sense as I didn't put enough examples on this page. So next class we'll do more examples for sine. But for now, let's just go through a few. If you feel a little shaky at the end of class, don't freak out. We'll do more practice tomorrow. Okay, first example, we want to find the sine inverse of negative 3 pi over 2. Okay, so sine inverse, this is the same thing as saying sine of what equals negative 3 pi over 2. Remember, we're just switching up the x value and the y value, okay? Okay, well, let's take a look at our unit circle. Any angles that are between, or any angles that give us the sine of negative 3 pi over 2? 4 pi over 3. Actually, no, I think you were right?
Oh, wait, yeah, my pen did.
No, let me write. I think I heard a 4 pi over 3, and I think I heard a 5 pi over 3, right? Okay, so we've got two answers here. Here's where things get a little bit tricky, okay? And before we go on, what I'm gonna do is I'm just gonna draw a picture of the unit circle, okay? Just a very bad picture. Okay. So it's just the axis and the circle in the middle. Okay. Let's talk about the possible answers that we can get here, okay? I told you that the only answers possible are between negative pi over 2 and positive pi over 2, right? Okay. I know where positive pi over 2 on the graph is, right? It's at the 90-degree angle, right? That's where positive pi over 2 is. Where is negative pi over 2? It's at the, yeah, it's like the other way around. It's at the bottom, right? Because negative angles go in a clockwise direction. So we're just reading the circle in an opposite way. So this right there is negative pi over 2. Okay. What I've told you is that the answer has to lie between negative pi over 2 and positive pi over 2, right? What quadrants are between negative pi over 2 and positive pi over 2? First one and the fourth one, right? No, you said the opposite. That's okay. Like this one's between negative pi over 2 and pi over 2. Also, quadrant 4 is between negative pi over 2 and positive pi over 2. Yeah, so let's take a look. So you said 5 pi over 3 definitely is between negative pi over 2 and positive pi over 2. That's good. But is 5 pi over 3 actually an angle between negative pi, like is that between the two numbers, negative pi over 2 and pi, oh my gosh, pi over 2? I think it was 5 pi over 3, right? That's 5 pi over 3. Okay. But is that number between negative and, huh? Yeah, right. So let me give you two options. Okay. Let me show you. Yeah, the highlighted ones does mean that it makes it, right? But 5 pi over 3, does anyone have a calculator that like has pi in it? Okay, let me, what does 5 pi over 3 equal in like decimals? Okay, 5.23. Okay, now give me what pi over 2 is in decimals. Okay, and negative pi over 2 is like negative 1.57, right? Okay, is 5.23 between negative 1.57 and positive 1.57? No. Okay, so it's definitely there. It's in that, like, it's in that highlighted space, but is it, how do we get it in between negative pi over 2 and pi over 2? It is negative pi over 3, and how'd you find that?
I don't know.
You read it backwards, right?
Yeah.
Okay, so you took the unit circle and you realized if you went clockwise, it's just going in the negative direction. So you saw, okay, we're going pi/3 in the clockwise direction. So I think Cole just saw, okay, this is negative pi/3. That's option number one. If you're comfortable with that, totally fine. Anyone know a different way to get an angle that represents the same point, but it's like a different number? Like coterminal, right? Yeah, so we're either going to add 2 pi or we're going to subtract 2 pi. Which one do you think we're doing this time? Subtract, right? Because we want to get a number like that's negative, right? Okay, so we're going to take 5 pi/3 and we're going to subtract 2 pi. Okay. Okay, 5 pi/3. What's 2 pi as a fraction over 3? 6 pi, good. So 5 pi/3 minus 6 pi/3 is negative pi/3. Okay. I got negative pi/3. It's the same thing as looking at your unit circle and looking backwards. I kind of prefer this option just because I don't feel like memorizing all the different ways to do this. But negative pi/3 is where you should get here. Okay. So let's just go back and see what we did. Okay. We rewrote sine inverse as like the way we like to think of it. Sine of what angle equals negative 3 pi/2. We got two different angles, 4 pi/3, 5 pi/3. And we knew our answer had to be either in quadrant 1 or quadrant 4. Okay. We got the angle that was in quadrant 4, but we realized it wasn't like between negative pi/2 and positive pi/2. So we subtracted 2 pi to get negative pi/3. Okay. Any questions on what I did there? Okay. Try example 3. I think it's a little bit easier because we don't have two answers. We just have one. I'll give you a few minutes on this, then we'll come back in a tiny bit. I know I didn't give you much time to work on this, but let's just go to the front. I promise you we will do more practice on this tomorrow. So if you're feeling a little shaky, don't worry yet. Okay. Let's just go to example number 3 now. Okay. Remember, sine inverse of -1 is the same thing as asking sine of what equals -1, right? That's all we're asking ourselves. Okay. Let's take a look on the unit circle. Okay. Okay, where on the unit circle is the sine equal to -1? 3 pi/2, right? So it's this angle right here. Oop, I meant to draw that in a better color. There we go. So 3 pi/2 is definitely what we're looking at here, right? Okay. Now remember, we're only focusing on quadrant 1 and quadrant 4. I forgot to mention that the boundaries do count. So even though it's like not technically in quadrant 4, it's still pretty close. It's like on the boundary of it. So that looks good to me. Is 3 pi/2 between negative pi/2 and positive pi/2? Technically, yes, but is the number between those two values? No, right? Okay. So definitely not between negative pi/2 and pi/2. What do you think we should do? Should we add 2 pi, subtract 2 pi? Subtract, right? If we added, then we just get further from pi/2, right? So why don't we just subtract 3 pi/2 minus 2 pi? Okay. And let's see, 3 pi/2 is good. What's 2 pi as a fraction over 2? Not 6 pi, 4 pi. That's good. I make that mistake all the time. And 3 pi minus 4 pi is negative pi/2. That is what we want. Okay. And let's see, that's an angle between negative pi/2 and positive pi/2, right? So we're good. I know I said between, I do mean including, okay? That I know it's a little confusing, but technically pi/2 is between negative and positive pi/2. Let's just take that as our answer, okay? One other thing you could have done, if you don't feel like doing the subtraction, you could have just solved 3 pi over 2 and realized it's going pi over 2 in the negative direction. Okay, so if you want to go a little bit faster, you can always just read it in the negative direction. Totally fine with me. But that's how we go here. Okay. Any questions on example 2 and example 3?
So for some, they always are gonna be in 1 and 4.
Uh,
1 and 4.
1 and 4, yes. Mhm. If you're a little shaky on this, don't worry. We'll do more examples of this next class. So don't freak out if you're feeling a little shaky. We'll get better at this tomorrow. But I do want to introduce cosine today, just so we can do more practice tomorrow. Okay. Cosine goes like the same way as sine. Okay. Let's just draw what cosine is. I'm gonna blast through this a little bit because we did go over the graphs today. But remember, cosine goes down, it continues going down, and it goes back up. Okay. And remember, cosine is a repeating function, so we can literally just repeat the same thing on the other side. I'm really bad at drawing. Okay, but this is what cosine looks like. Okay, cosine, does it pass the horizontal line test? No, right? It definitely doesn't have an inverse on its own. Let's try restricting the domain the same way we did last time. Okay, so let's say we want to restrict the domain between negative pi over 2 and pi over 2. And let me just highlight that area. Does that pass the horizontal line test? No, right? Huh. So it seems like we can't restrict the domain in the same way as we did with sine, because doing that doesn't help us at all, right?
So it's 0 to pi.
Yes, perfect. Between 0 and pi, looks like we have something going straight down. It doesn't curve up, so it looks like we have an inverse between 0 and pi. Okay, now technically, we could also restrict the domain using different areas like negative pi to 0, negative 2 pi to pi. But remember, the important ones, well, the most important point for most applications always includes 0, right? 0 is usually something that happens a lot in real life. So we're going to restrict the domain between 0 and 2 pi, or sorry, 0 and pi. Okay. So when we restrict our domain, the graph of cosine is literally going to look like this between 0 and pi. And the answers for cosine are always going to be between 0 and pi. That's where our answer is always going to lie between. Any questions on cosine? Okay. I think what we'll do is we'll do a few more sine practices tomorrow. We'll go do cosine after it because I think cosine's a little bit easier. And yeah, I think I'll leave it here. So if we have no questions, then you are free to go. We'll be meeting in Double Bis Hall tomorrow. So I have not yet come to the wrong classroom yet, but we'll see how that goes tomorrow. Have a great rest of your day. I'll see you tomorrow.